En Fundación UNAM seguimos trabajando por la cultura, la ciencia y la educación. Sin salir de casa, podrás reflexionar con los martes de ciencia, a través de las conferencias de Universidades por la Ciencia que emitimos todos los martes en punto de las 12 horas. Disfrutarás con la segunda edición del ciclo de documentales Nuestra Nueva Realidad, emitido en conjunto con TV UNAM los jueves a las 17:30 horas. Para reflexionar, tienes las actividades del Corredor Cultural de Autonomía sobre las afectaciones de nuestra nueva realidad en distintas disciplinas. Y como cada mes, sigue las conferencias de Ante la Nueva Realidad, Hablemos de Cultura. Sigue nuestras redes sociales y no te pierdas ningún detalle en www.fundacionunam.org.mx.
El chile representa, junto al maíz, tomate, frijol, cacao o vainilla, entre muchos otros productos, la milenaria cultura culinaria de México. Los mexicanos no podemos imaginar una comida sin alguna salsa o un chile de cualquier tipo. El chile es uno de nuestros símbolos nacionales y como tal, debemos apoyar su cultivo, uso y exportación, otorgándole así el lugar que merece este particular y sabroso fruto ardiente.
En Fundación UNAM seguimos trabajando por la cultura, la ciencia y la educación. Sin salir de casa, podrás reflexionar con los martes de ciencia, a través de las conferencias de Universidades por la Ciencia que emitimos todos los martes en punto de las 12 horas. Disfrutarás con la segunda edición del ciclo de documentales Nuestra Nueva Realidad, emitido en conjunto con TV UNAM los jueves a las 17:30 horas. Para reflexionar, tienes las actividades del Corredor Cultural de Autonomía sobre las afectaciones de nuestra nueva realidad en distintas disciplinas. Y como cada mes, sigue las conferencias de Ante la Nueva Realidad, Hablemos de Cultura. Sigue nuestras redes sociales y no te pierdas ningún detalle en www.fundacionunam.org.mx.
Bienvenidos al ciclo de conferencias de Universidades por la Ciencia, organizado por Fundación UNAM y un conjunto de universidades, incluyendo la Universidad Nacional en México y en el extranjero. El día de hoy tenemos una conferencia muy especial a cargo del profesor Christopher Hood de la Universidad de Bath en Inglaterra, quien es además el director del Centro de Mecánica No Lineal y es el director también de la parte de matemáticas en la Royal Institution en the UK. Es un verdadero placer el agradecerles y que nos acompañen semana a semana. En el presidio nos acompañan el presidente de la Fundación UNAM, Dionisio Meade, la directora ejecutiva de Fundación UNAM, Araceli Rodríguez, el profesor Kirill Chernichenko de la Universidad de Bath y Araxi Urrutia también del Consorcio de Universidades por la Ciencia, y nuestro invitado de lujo, el profesor Christopher Ppo4. Welcome to this seminar series of the Consortium of Universities for Science. Today we have a very special conference by Professor Christopher Ppo4, who is a professor in the University of Bath, the chair of mathematics in the Royal Institution, and a very well-known mathematician. And we thank him for joining us today. The University of Bath is part of this consortium of universities for science, and the presentation will be by the Professor Kirill Chernichenko. This seminar series is organized jointly by the Universidad Nacional Autónoma de México, the Institute of Applied Mathematics, and the Instituto de Innovación Matemática in the University of Bath. It is a pleasure to thank you all of you, and we are looking forward for this conference on mathematical models of the ice ages. La plática es sobre los modelos matemáticos de las edades glaciales, y es parte de lo que desde la antigüedad ha sido una de los intereses de las diferentes culturas. La regularidad en que ocurre el día, la noche, el movimiento de los astros, y es nuestra medida de tiempo. Los días, las semanas, los meses están ligados a los ciclos del Sol y de la Luna, y esto se refleja en lo que tenemos también en la parte de cambio climático. Voy a agradecerles, voy a pasar la palabra ahora a nuestro presidente de Fundación UNAM, licenciado Dionisio Meade. I will introduce Professor Meade to give us the welcome to Professor Christopher Ppo4.
Muchas gracias a todos. Nuevamente les damos la bienvenida a este ciclo de conferencias que estamos llevando a cabo en el marco de Universidades por la Ciencia, de este consorcio que se ha establecido y que fue una respuesta muy constructiva, muy oportuna, muy pertinente después de la parálisis que generó en la comunicación la pandemia que arrancó el año pasado. Esto, la verdad, nos ha abierto muchas puertas, ha traído consigo esta idea formidable de crear el consorcio. Damos una posibilidad de intercambio de conocimientos, de intercambio de información, con una ventaja que nosotros siempre subrayamos. Se trata de investigaciones en curso. Esta presentación, además, hemos querido inscribirla en lo que nosotros llamamos pues el marco de una nueva realidad. Pensamos que después de la pandemia tenemos que insertarnos en un mundo diferente, en un mundo que no será el mismo y en el cual se ha acreditado por la propia experiencia de la pandemia que el respeto por la ciencia es uno de los postulados que hoy subsiste con mayor vigor, y otro de ellos es el mejor conocimiento del planeta. Yo creo que debemos celebrar que tengamos la oportunidad de este intercambio y que veamos en el marco de esta nueva realidad cómo este conocimiento que hoy se nos va a presentar nos ha de llevar a que tengamos un mejor cuidado del planeta. Y yo creo que uno de los temas que mayormente inciden en esta nueva realidad es qué tenemos que hacer con el cambio climático. Es un dato duro que el cambio climático ha venido imponiendo sus reglas, que tenemos que enfrentarlo, que tenemos que darle cauce, y pláticas como estas nos obligan justamente a reflexionar mejor cuál es el futuro del planeta, el futuro de esta casa común. No tenemos otro, aunque ya tengamos experimentos en Marte, esta sigue siendo nuestra casa común, el lugar donde tenemos que cuidarnos, el planeta que tenemos que preservar. Las comunicaciones que tenemos a través de estos consorcios tienen la gran ventaja de que rompen fronteras. No estamos confinados a la capacidad del auditorio. A través de las redes podemos abrir la comunicación a muchísimos espacios, a muchísimos lugares. Y estamos seguros que nuestro auditorio de hoy recoge interesados en el avance de la ciencia, tanto en nuestro propio país, en los universitarios, en los estudiantes y académicos de la Universidad Nacional, como sin duda lo son también estudiantes académicos y investigadores de la Universidad de Bath y de otros muchos que forman parte del consorcio. De manera que creemos también que este espacio que se está realizando a través de este ciclo de conferencias está significando una experiencia inédita, una experiencia formidable que puede potenciar en mucho este intercambio de información y de conocimientos que se abre con la posibilidad de que todos nos digan lo que saben y entre todo ese saber de muchos vayamos construyendo ese mundo mejor para nuestro país y para el mundo que la humanidad se merece. Gracias de nuevo a Christopher Bott por su presentación, gracias a quienes desde el consorcio, de manera particular a Jaime y Araxi, Jaime desde el Colegio Nacional, desde la trinchera de la propia universidad, Araxi también, con esta idea formidable y que contribuyen semana a semana a enriquecer nuestro acervo de información, nuestro acervo de conocimiento y sobre todo nuestro acervo de estímulo a la investigación. Siempre pensamos que uno de los frutos de estas pláticas será que muchos jóvenes de todos los países, porque ahora se abre este espacio de comunicación en muchos frentes, se sumen a este interés por la ciencia. Hace 2 semanas tuvimos la presentación de William Phillips, que nos hablaba, premio Nobel, que nos hablaba de esta necesidad de estimular a los jóvenes a participar más activamente en la investigación, en el desarrollo tecnológico, y él nos decía cómo sembrar esta semilla de curiosidad, de preguntarnos cada vez cómo y por qué, es precisamente el germen que abre las puertas de la ciencia. Gracias a todos y esperamos con mucho interés la presentación del profesor Bott para escuchar sus comentarios, su enseñanza y cómo se inscribe en la nueva realidad del cuidado del planeta la presentación que hoy nos va a hacer. Gracias de nuevo.
Hello, everyone. I'm Kirill from the University of Bath, and it's a special pleasure to introduce our speaker today, my colleague from Bath, Professor Chris Budd. Professor Budd gained his undergraduate degree from St. John's College, Cambridge in 1982, where he was senior wrangler, meaning he was top of the class in his year. He went on to be awarded a DPhil from Oxford in 86, studying numerical methods for nonlinear elliptic partial differential equations under the supervision of John Norbury. He then spent 3 years as a fellow of St. John's College, Oxford, working in numerical analysis at the Oxford University Computing Laboratory, and as a fellow sponsored by the Central Electricity Generating Board, developing numerical methods for third-order partial differential equations. He went on to a permanent post as a lecturer in numerical analysis at the University of Bristol, before gaining a position as professor of applied mathematics at the University of Bath in 1995. He was appointed the professor of geometry at Gresham College in 2016, where he delivered a series of public lectures on mathematics and the making of the modern world. Since 2015, he has also served as professor of the public understanding of mathematics at the International Centre for Mathematical Sciences in Edinburgh. Professor Budd's research interests involve the analysis, application, and numerical analysis of solutions to nonlinear differential equations, with a particular emphasis on problems which arise in industry. Some of his recent work has been in geometric integration, which aims to develop numerical methods that reproduce qualitative structures in differential equations. He is the director of the Interdisciplinary Center for Nonlinear Mechanics at the University of Bath, and the director of Knowledge Exchange of the Institute for Mathematical Innovation, who is one of our sponsors, and is active in promoting interdisciplinary collaboration both nationally and internationally. Professor Budd is a passionate popularizer of mathematics, reflected in his appointment as chair of mathematics of the Royal Institution of Great Britain in 2000. He works on a number of projects with schools and has written a book, Mathematics Galore, based on his series of popular talks. He has also made numerous guest appearances on national radio and television, such as on the BBC's The One Show and popular science panel comedy game show, It's Only a Theory. He won the Leslie Fox Prize for Numerical Analysis in 1991, and in 1999 he was one of the 10 scientists awarded the title of Scientist of the New Century by the Royal Institution. In 2001, he was one of the 20 lecturers in the UK to be awarded an Institute for Learning and Teaching Fellowship, and he was nominated the London Mathematical Society's Popular Lecturer in Applied Mathematics. He was awarded the Order of the British Empire in the Queen's Birthday Honours List in 2015 for services to science and maths education. He has supervised 32 PhD students to completion and is currently supervising 9 more. Most recently, he has been awarded University of Bath Chancellor's Prize for Leadership in Public Engagement. It could pretty much take most of our time today to look at Professor Barth's many academic achievements. I haven't mentioned his many years of work with the London Mathematical Society, Institute for Mathematics and Applications, Royal Society, European Mathematical Society, or appointments as panel member for the UK Research Evaluation Framework. Chris has been very active in the mathematical modeling of COVID-19 and is one of the leaders of the VCAMS, which stands for Virtual Forum for Knowledge Exchange in Mathematical Sciences, currently focusing its efforts on the pandemic. I'm grateful to Chris for agreeing to share with us today some of his passion for mathematics and its applications. So I'll be stopping here and passing it over to him for his lecture on mathematical models for the ice ages. Just a quick note, as usual, questions are very welcome in the chat during and after the lecture. Over to you, Chris.
Well, Kirill, thank you. That's very, very kind. And of course, the thing I'm most proud of is being a colleague of such wonderful friends at the University of Bath. And it gives me very great pleasure to be able to use the technology of Zoom to join you over in Mexico. And I hope that one day I shall come and visit your wonderful country. So one of the areas that I've been working in a great deal for the last few years has been understanding climate change, both climate change happening now and also climate change which happened in the past. And as part of this, I work a lot with the United Kingdom Meteorological Office. And I want to talk today about some what I call conceptual models for climate change, how mathematicians basically try to understand climate change through mathematical equations. And then in particular, I will look at the ice ages, which were the kind of dramatic variations in climate that we've had over the last million years. And in particular, I'm going to talk about joint work I've done with a wonderful student of mine called Susan Moripisi, who came over to Bath from Botswana on a scholarship from the University of Botswana and came from a very hot country to study the very cold problem of ice ages. And she's now back in Botswana, where she's a university lecturer at that university. So let's talk about mathematical models of climate. And basically, there are two ways that we can try to predict the climate. There's an organization you may have heard about called the International Panel for Climate Change, which is the organization which tries to present the scientific evidence for climate change to politicians all over the world. And every 4 years, they publish a humongous report about the latest predictions of the climate models. And the way they do this is they construct extremely sophisticated models which try to account for everything they can possibly think of. And then these models are put on the largest computers that they can think of, computers so large that they produce enough heat to be a factor in global warming. And then these produce predictions which are very detailed over the next 100 years or so. And because these models are very, very sophisticated, they're actually quite hard to test. And also, they cannot be run to look at the climate over long periods of time. It's just too expensive and burns the computer up too much. So there's another way we can look at climate, which I will call the mathematician's way, which is, instead of using hugely sophisticated models which have every detail in under the sun, literally, what we're trying to do is construct reduced models which have enough detail in them to make predictions with, but not so much detail that you can't do analysis with. And these models are very useful because we can then predict the climate over much longer periods, and also they make predictions which in a way can help verify the much more sophisticated models that are used to make the very detailed predictions that are used to advise governments. So method 2 is mostly what I'm going to talk about today, but I'll just have a quick look at the way that very sophisticated climate modelling works and the way that we have to kind of work when we advise politicians and other policymakers. So modern climate models, as I say, are very highly sophisticated things, and they are run on very, very large and powerful computers. And when you advise a government, they don't want to know what the climate's going to do in the next 100 years. They want to know what the impact of climate change is on humanity. So bottom right in this picture are the sort of various climate models, which model things like the oceans and the atmosphere. And then those climate models feed into what are called integrated assessment models, which look at the impact of climate on things like the economy and health and so on. And some of the work that I'm doing with my PhD students in Bath is looking at the impact of climate on changes of energy and also on agriculture. And then from looking at the way the economy and energy changes, you then look at the hardest thing of all, which is how human beings are going to react to climate change, how it's going to change the way that we live. And putting all that together, we have what's called an Earth system model, which is a hugely sophisticated thing, which is used to tell our governments what the impact over the next 100 years of the changes in climate will be. So that's what's going on. And the sort of models that are used by scientists are basically of two types. You have physical models where you literally in a laboratory try to build what's going on in the climate. But mostly what I'm going to talk about today are what we call mathematical models, where we're trying to simulate the climate using mathematical equations. And we can either look at static climate, what is the climate going to do over a short period of time, or dynamic, what it's going to look over a longer period of time. And all of these, and then a combination of mathematical analysis and numerical work. And ultimately, we try and simulate the climate system. And there are what we call a hierarchy of different types of climate model. And I'm going to explore this hierarchy in this talk, where my two axes here are the x-axis is the level of detail that you put into the model, and the y-axis is the number of things that you kind of think about. And top right are the ones that I just described, the Earth system models. And feeding into those are what are called general circulation models, which can either look at the atmosphere and ocean, or the atmosphere and the ocean separately. Feeding into those are models of intermediate complexity. Feeding into those are what we call box models, where you divide the Earth up into a number of boxes. So one of the problems I'm working on at the moment is looking at the circulation in the Atlantic. So we take the Atlantic as one box, take the Pacific as another box, take the Indian Ocean as another box. And feeding into these are the simplest models of all, which I will describe in this talk, which are called energy balance models. So here's our hierarchy, and each model feeds into the next one. And sometimes when you have a model you don't understand, which is kind of an intermediate one, when you're not putting in all the detail, you may include what we call stochastic effects, that sort of randomness, to try to account for things that you don't really model at that level of detail. And this hierarchy is absolutely needed, because without the simpler models that you can test and try to understand analytically, you've no hope of knowing that the really sophisticated ones are doing their job. So it's absolutely vital. So just to put that in words, at the one end of complexity, we have general circulation models, which are used by the IPCC to make precise predictions over decades, looking at the whole Earth. And then feeding into those are the models of intermediate complexity, which is what I'm partly going to talk about today. And these are useful for looking at things like ice ages, El Nino, which presumably may be relevant to Mexico, maybe not so sure, but the ocean currents in the Atlantic, which certainly are relevant to Mexico. And then the energy balance models, which are the simplest ones. Okay, so that's the kind of theory. Let's look at the practice. As I say, I spend a lot of my time working with the Met Office, that's the Meteorological Office in the UK. And the Met Office has to provide weather forecasts, and it provides a weather forecast every 6 hours. And a typical weather forecast will tell you what the weather will be over the next week. And the codes that they use are in the circle on the bottom left of this picture, which are very, very detailed. They give predictions over a length scale of about a kilometre and a half, and work up for about 7 days in advance, and are tested rigorously every day. So if they forecast the weather and the weather is wrong, you know it instantly. And the one that is most used is called MOGREPS, which, well, I won't go through the letters, but anyway, that's what is done. On the top right, we have the models that are used for climate modelling, which are done by an outfit called the Hadley Centre. And the Hadley Centre is part of the Met Office, but they just do the climate work. And the most sophisticated model they have is called HadGem3, and that makes predictions up to about 100 years, and that the resolution they have is about 25 to 50 kilometres. So this is the actual what's going on the ground, as it were. And some of the work that I do with my team is we advise the Met Office on how to make their models run faster, basically by making the computer algorithms more efficient in terms of how they solve their equations. Okay, so that's the kind of Met Office hierarchy. But let's start now with actually doing some analysis of some of the actual models that we're going to study in this talk, looking at, to start with, the simplest, and then working up to some more sophisticated models which we can use to predict the ice ages with. So the simplest models that are used to predict the climate, remarkably accurately, considering how simple they are what are called energy balance models. And these models go back to the 19th century and were introduced originally by Arrhenius. And anyone that studies chemical reactions will know the name Arrhenius because his name is attached to the main mathematical equations for chemistry. And Arrhenius postulated, very simply, that the Earth receives energy from the sun, and some of that energy gets reflected immediately by the clouds in the atmosphere, and some of it then gets towards the Earth itself. And when it gets to the Earth, it heats the Earth up, and then the Earth re-radiates that energy, and that energy, some of which goes back into the atmosphere, heats up in the atmosphere and gets re-radiated back to the Earth, and some of it gets back into space. But if you add up the total amount that goes into space from the Earth, either by being reflected from the clouds or being re-radiated, then that must equal the amount of energy coming in from the sun. That's called a flux balance. It must be right. Energy goes in, must equal energy going out. And sort of rough average, the amount of energy coming in from the sun is 342 watts per meter squared, and that is averaged over the entire surface of the Earth and averaged over day and night. And 107 watts per meter squared is immediately re-radiated, and 235 watts per meter squared is radiated, having been absorbed by the Earth. And what makes this model kind of interesting is that the way the Earth absorbs and re-radiates heat is different. So it absorbs energy from the sun in short wavelengths, basically light, and it re-radiates the Earth in long wavelengths, which is basically infrared. And short wavelengths are not particularly absorbed by the atmosphere, but long wavelengths are very much absorbed by the atmosphere. And the absorption of the long wavelengths by the atmosphere is very much affected by the amount of carbon dioxide in the atmosphere. And that is why carbon dioxide production by humanity is so important in understanding how the Earth's temperature changes. So those are the various bits of energy going in. I should say this graph is nothing to do with me. This is a graph produced by the Hadley Centre, picture produced by the Hadley Centre. But just to do a bit of math, the key thing to heat up the Earth is S of T, which is the amount of radiation coming in from the sun. And you divide that by 4 to give the average over the entire Earth's surface. And then you multiply that by a factor 1 minus A. A is called the albedo. That's the amount of energy which is reflected immediately back from the Earth. So 1 minus A is the amount that's absorbed by the Earth. So A is something like 0.4. The temperature of the Earth is TG, that's the ground temperature of the Earth. And the Earth, roughly speaking, acts like a black body. So the amount of energy it radiates is proportional to the 4th power of the temperature multiplied by a number called sigma, which is called the Stefan-Boltzmann constant, which is just a number. But multiplying all of that is the rather interesting factor 1 plus Tor LW divided by 1 plus Tor SW, where Tor SW is the transparency of the atmosphere to shortwave radiation. So that's how much radiation gets through the atmosphere at short wavelengths, which is 0.9, so nearly all the radiation gets through. And TLW is the amount of radiation which is absorbed in the long wavelengths, and that's about 0.2. So there we have it, and the equation for flux balance can then be simplified to E times sigma times T to the 4th, where E is this number 1 plus Tor LW divided by 1 plus Tor SW, and we get the equation for the temperature at the bottom. And I like this equation. This is an equation I can go into a school and explain to a high school student fairly easily. I can tell them what the numbers for A and E are that can be measured in the laboratory. They know what S is by, we know how much energy is coming from the sun. And you plug all these numbers in and you take the 4th root and out drops the temperature of the Earth. And it's right. And it's kind of exciting that such a formula can predict that. Similarly, if I say, well, let's go to the moon. So in the moon, the E, which is called the emissivity, is how much of the radiated energy gets back into space. For the moon, E is 1. And if you plug that in, you get the mean temperature of the moon. And that's again it. And it's right. And it's the students get very excited that they can predict the temperature of the moon from one formula without even going to the moon. You can also use this formula to make predictions with. So the critical number in this equation is the number E, which is the proportion of the energy produced by the Earth which gets radiated into space, which is currently about 0.4. Now, as you increase the amount of carbon dioxide in the atmosphere through industrial pollution or whatever, then the amount that gets into space is reduced, so E goes down. If you look at the formula for T, if E goes down, then T goes up. That's there in the math. You can't miss it. So if E goes down, T goes up, and therefore if E goes down due to carbon dioxide, the Earth's temperature goes up, and therefore we get a hotter Earth. And that is global warming in a formula. Now, when I give talks on climate change to other audiences, and this one I'm sure I get abusive emails and abusive things posted on my website telling how stupid I am, and that the Earth is cooling and there isn't climate change and all that. And I simply go back to this formula. That formula tells us there's no way around it. There is the Earth is heating up because E is going down, and E is going down because carbon dioxide is going up. It's as simple as that. So that's the flux balance equation. Now, there are various ways of making this equation a bit more interesting and a bit more realistic. And in the 1960s, two rather sensible people called Boudico and Sellers saw a way of improving on this formula. And their idea was this, that the Earth's albedo, that's how much it reflects, changes with temperature. And the reason for that is simple. If the Earth is very hot, then all the ice in the Earth vanishes. And one of the main things which reflects the sun's energy is the ice in the Earth. So if there's no ice, then much less energy gets reflected, so more gets absorbed. In comparison, if the temperature of the Earth is very cold, then the ice, there's lots of ice on the Earth, and the albedo is then very high because much less Earth temperature gets, all of the sun's energy gets reflected, and some 1 minus a is smaller. So if you plot a graph of 1 minus at, and here I've got 3 graphs, but the green one is kind of interesting, and you plot the graph of E sigma t to the 4th, you find that you get 3 points of intersection between this graph of 1 minus a, actually it should be 1 minus a times s, I apologize, and E sigma t to the 4th. And that implies that the Earth can exist in either a very hot state or a very, very cold state. The cold state is often called snowball Earth, and the hot state is I'm not sure it's called anything. Anyway, very hot Earth anyway. And that is consistent with observed data. If you look at the climate data going back over billions of years, there have clearly been times when the Earth has been very, very hot and stayed hot for a long time, and other times when it's been very, very cold and stayed cold for a long time. And here's a graph that's a prediction of the Boudico-Sellers model, showing that you can have the Earth, which is completely covered in ice, which is stable. It can be very hot, which is also stable, and there are various unstable bits in the middle. And that's the Boudico-Sellers model. And that is, I say, consistent with observed data. And for a while, it was thought that this was also consistent with what happens in ice ages. So top left is an interesting picture. These are experimental pictures showing rapid transitions of the Earth going from one state to another at the either beginning or end of ice ages. And that is sort of consistent with the fact that you've got these possible multiple states predicted by the Boudico-Sellers energy balance model. But just to show you that climate science is an evolving science, we don't believe this anymore as an explanation. Basically, the Earth would have to change an awful lot in order for this explanation to be right. And whilst that might explain various things that have happened billions of years in the past, it's not a very good explanation for the ice ages as we've seen them in the last million years. And that's what I want to talk about for the remainder of this talk. So I want to tell you now about the ice ages. Now, let me explain how we know that there have been ice ages. Well, for one reason, we know that we had an ice age about 20,000 years ago because we can look at evidence from human people in caves who drew pictures on the caves clearly showing that the Earth was cooler then. But if you want to go back much further into the past to find out what the Earth's temperature was doing, you have to do what we call proxy measurements. And the usual thing that's done is that people will go to either Greenland or Antarctica and they drill down into the ice. And as you drill down into the ice, every year the ice has a different layer. You can see the layers very regularly, one after the other, and you can count them. And you can measure the amount of oxygen-18 isotopes. So oxygen has various isotopes. and you can measure, the normal one is oxygen 16, but there's also an isotope called oxygen 18, and you can measure the amount of oxygen 18 in the ice, and that tells you basically what the temperature is, because as the temperature varies, the proportion of oxygen 16 and oxygen 18 varies, and so by measuring that, you can work out what the temperature is. So the top graph in blue is the mean temperature of the Earth over the last 500,000 years ago from an ice core called the EPICA ice core. The green curve is the mean temperature of the Earth taken from a quite different ice core called the Vostok ice core. And underneath is measurements. You can basically measure this by looking at the sediment in the sea and so on, about the total amount of ice. So the blue curve and the green curve show temperature, with temperature increasing from bottom to top, and the bottom curve shows the amount of ice, with top being the low amount of ice and bottom being a high amount of ice. And what's very striking from these pictures is that there's quite a regular pattern. So basically, the Earth's climate seems to have cooled slowly and then heated up rapidly, and then cooled slowly and then heated up rapidly, and then cooled slowly, heated up rapidly, cooled slowly, heated up rapidly. And you get these very characteristic cycles. And these are called glacial cycles. So a glacial cycle is the period of rapid warming followed by long cooling. And an entire glacial cycle takes around about 100,000 years. And about 10,000 years ago, what's called the end of the Dryas period, the Earth's temperature increased, and we're now in a period of a warm period called the Holocene. And this is very important because human civilization, growth of cities and agriculture all happened after the end of the last ice age, so around about 10,000 years ago. And if the Earth was left to itself, we'd expect it now to be starting to cool as we go into the next ice age. Instead, we see the Earth warming up, and that's because of the effect of humanity. If you look at the bottom graph, you see that the total amount of ice basically increases as the Earth cools and then suddenly decreases as it warms up. And the ice volume is very much in step with the temperature. So one of the very interesting questions we want to understand is why the Earth's ice ages occur and why they have 100,000 years periodicity. But the story is a bit more interesting than that. Here's a picture of the Earth's climate where instead of going back a million years, we go back 5.5 million years. And the Earth's climate seems to have gone through three phases. Up to about 3 million years ago, it was more or less staying the same. It jiggered up and down a bit, but more or less staying the same. Then from 3 million years to 1 million years ago, we had moderate oscillations with a period of 41,000 years. And we know why those occurred, and I'll show you why in a minute. And then from 1 million years onwards, we go into these large oscillations with a 100,000 year cycle. And that's where we are now. Well, we'll just come out of one. And a million years ago, something happened. It's called the Mid Pleistocene Transition, where the Earth's climate changed from being 41,000 years periodicity of low amplitude to 100,000 year periodicity of large amplitude. And what we want to try to understand when we look at the ice ages is why the Earth's climate varies and why we got this change about 1 million years ago, and why we are currently in a state where the periodicity is about 100,000 years. This is a wonderful question. And although we're looking back in the past and trying to make measurements in the past, this is important for the future because by understanding the ice ages, we might get a better understanding of what our own climate's going to do, even in the next 100 years. For example, what will happen if we melt all the Arctic ice, which is quite likely to happen in the next 30 to 50 years. Okay. Now, in the 70s, it was thought that there was an explanation for this, and I'll tell you what that is in a minute. But let's have a quick look at all the things which might make up an ice age. One is that you get a change in the output of the radiation coming into us from the sun. Secondly, you've got the amount of ice on the sea. Secondly, the amount of ice on land. These are the glaciers. Then you've got the amount of carbon dioxide, then the temperature, and then big things like continental drift. And in practice, we're going to cut a coupling of all of these, which are going to produce the ice ages. But as I say, in the 1970s, it was thought they sorted it out. It was thought that the ice ages were entirely explained by the first of these, which is the variation in the amount of forcing you get from the sun, the amount of radiation you get from the sun. And here's a plot. In this case, we've got going into the past of the variation in the amount of forcing from the sun. And this is due mostly not due to the sun changing, but due to the Earth wobbling. So the Earth is a ball spinning on an axis, and that spinning ball goes around the sun. And if you take a top and you start it spinning, then the top will wobble on its axis. It will do two things. It will change its orientation going like this, and also the axis will change its orientation going like this. And these are called precession and obliquity. And the Earth goes around the sun in an ellipse, and the ellipse changes its eccentricity. So we're slightly nearer the Earth in the winter in the northern hemisphere, and slightly further away in the summer, again in the northern hemisphere. And if you put all these together, we know how the Earth is wobbled. You get what are called Milankovitch cycles, and the yellow curve shows the total solar forcing changing over the last million years. Incidentally, again, the climate skeptics that send me emails and write on my YouTube channel saying, well, it's obvious the climate's changing, it's due to Milankovitch cycles, forget about humanity, it's irrelevant. But the Milankovitch cycles are tens of thousands of years. What we're seeing at the moment is climate change over 10 years. It's a different mechanism completely. Okay, so in the 70s, books were written. A book was written saying the ice ages resolved. Problem done. It's all due to these Milankovitch cycles. But if you look at the yellow curve, underneath it is the amount of glaciation. This is the same picture that we had up earlier. You'll see that these don't particularly correspond very well. So there must be something else going on. Now, the dominant forcing, if you look at the actual amplitude, is the obliquity, which has a variation of 41,000 years. And before the Mid Pleistocene Transition, the variation in the Earth's temperature was 41,000 years. So we can well believe that that was due to changes in obliquity. But the 100,000 years, much harder to explain. So here we have the issues. We've got all these different frequencies in the Milankovitch cycles. The dominant frequency of 41,000 years seems to neatly explain what was happening to the climate before the Mid Pleistocene Transition. There is a forcing frequency which is nearer 100,000 years, which is eccentricity. But that is actually very, very small. It's much, much smaller than all the others, and it's not thought to be very important. So the very interesting question which we want to ask is, why do we have a 100,000 year cycle of the ice ages at the moment, and what causes this? And there are basically three different theories. The first is that it's an externally forced reason due to probably eccentricity, but we think that's unlikely because the eccentricity is so small. Secondly, it's got nothing to do with anything external. It's just an independent internal climate variation, which just happens to have a 100,000 year period. And thirdly, it's kind of a combination of the two. so that the dominant change is an internal one, but the Milankovitch cycles, what we call synchronize it, so they help it be 100,000 years. To give an example of this, the human body's natural, our natural cycle is about 25 to 26 hours. So if you leave someone in a cave and switch off all the lights, then they will have a 25 to 26 hour biological cycle. However, the normal cycle for a human being is 24 hours, and that's because our biological cycle gets synchronized by the solar cycle into being 24 hours. And my own view, and many other people's view, is that the most likely explanation for the ice ages is that we have a variation within the Earth, which is more or less 100,000 years, but it's actually synchronized by the Milankovitch cycles. So that's kind of a cosmic clock, which is kind of keeping things ticking over. And let's give some reasons for that. So there are basically two mathematical approaches which have been used to try to understand this, using these intermediate models of complexity, where the explanation for the ice ages is described using the mathematical theory of dynamical systems. So dynamical systems is just a fancy mathematical term for things which change in time. So it was dreamt up about, I don't know, 100 or so years ago by Poincaré, and is very, very a big area of mathematical investigation. A couple of weeks ago, we had the big dynamical systems conference in America, which we attended by Zoom, which had 1,500 people attend it. And there are two ways of trying to understand climate. One is to use what we call smooth dynamical systems, where we write down differential equations and try to explain the various types of dynamics in terms of oscillatory solutions to those differential equations, and we look for things called bifurcations for giving us the transitions. And the other type of explanation is to say, well, actually the climate has many different timescales, and if you think of the Earth's climate as evolving ultimately over billions of years, then anything which occurs on, say, a few thousand years is almost instantaneous and acts like a switch. And so it's probably better to try to explain the Earth's climate as dynamical systems with switches in them. And that brings us into the range of what was called non-smooth dynamical systems, which is a particular interest of mine, where you get transitions due to other reasons, which I shall talk about in a minute. So here are various models, and lots of mathematicians have been working very hard on writing down these different types of dynamical system to explain what's going on. So a very popular model, which I will call the smooth model for explaining the ice ages, is called the Saltzman and Marsh model. And this is a nice model. It's very easy to explain this to an undergraduate, and I've had undergraduates do projects on this model to kind of get a feel for how the climate might vary. So the Saltzman-Marsh model has three variables. V is the average ice mass over the Earth. C is the average carbon dioxide in the atmosphere. Capital T is the average temperature of the deep ocean. And then you've got this sort of fancy set of equations with various quadratic and linear terms. And you have two forcings, a fast forcing S of T, which is the Milankovitch forcing coming in from the sun, and a slower one, F mu of T, where the idea is that as the continents move around, so things slowly change. Ocean currents slowly change, or the amount of carbon dioxide coming in the atmosphere from volcanoes slowly change. So there's a model, and by waggling around the coefficients enough, you can get this model to have periodic solutions, and you can get transitions. So here's a picture. These pictures show you what happens as you vary the slow force of F mu, and you can go from a steady state, which is the black curve, into a periodic cycle, which is the red, and then back to steady state. And if you're clever, you can even waggle it so that you get different types of oscillation. So this is a model for the ice ages. It gives a certain amount of predictability. It uses the theory of smooth dynamical systems. I'm not completely convinced by it. The model here was largely constructed out of thin air, as far as I can tell. And by choosing your parameters, you can certainly get it to behave any way you want. So there's no real justification for it. And unfortunately, a lot of climate modelling is like this. I'm not saying the models I produce are any better than anyone else's. The basic problem is that we can't go back a million years to see what's actually going on. So to a certain extent, we have to construct models and try to justify them as well as we can and see whether they agree with the actual observed data. But until we can go back a million years, we're never going to know for certain. Unless, of course, we have another ice age in the future. And we can see it going on. You know. Okay, so that's a smooth model. Let's look at now in contrast. Now, I'll talk about this in some detail. For a non-smooth model for explaining the ice ages, called the Ppo4 transition model, after two French mathematicians, Pallard and Perriman, who came up with this model in 2004. And I've actually worked on this. This is the model I worked on with Susan Morabisi, and we've published a couple of papers on this. And the idea in this model is that you have three kind of variables you're interested in. You have the ice volume away from Antarctica, V, the amount of ice on Antarctica, A, and the amount of carbon dioxide in the atmosphere. And you have firstly a cooling of the Earth, the glacial period, and during the cooling, the carbon dioxide in the atmosphere is absorbed into the ocean. Now, we know this happens. You can actually measure it happening. But when the carbon dioxide in the ocean gets to a certain amount and the ice on the ocean gets to a certain amount, which kind of destabilizes things, then the deep ocean becomes unstable and the carbon dioxide is suddenly released from the ocean into the atmosphere. Now, we know what happens when carbon dioxide gets released into the atmosphere. The energy balance model tells us that the atmosphere, the Earth will then warm up due to the greenhouse effect. So when the carbon dioxide from the oceans gets into the atmosphere, the Earth suddenly warms up. And that is what happens at the end of the ice ages. You get this deglaciation. And then when all the carbon dioxides come out of the ocean into the atmosphere, then the Earth starts to cool again and the carbon dioxide gets absorbed again, and you go through this cycle. So that's the Ppo4 model. Okay, I won't say anything more than that. I did not derive this model. I take the model and try to analyze it as well as I can. And if anyone's interested, the two papers, they wrote a paper in 1998 and 2004. Both papers got published in Nature, and they're very readable and try to explain the ice ages through that model. Right, let's do some math now. Okay, so next few slides are going to be a bit more technical because I'm going to show you the way that Susan Morabisi and I then went about analysing the Ppo4 model. So the Ppo4 model tries to explain the dynamics of the V, the ice volume, A, the Antarctic ice, and C, the carbon dioxide. And it's a model with three differential equations, just like Saltzman and Marsh. You've got the I-65 telling you the forcing due to the sun. But the crucial difference between this model and Saltzman and Marsh is that the carbon dioxide equation has a discontinuity in it caused by a Heaviside function. So the Heaviside function is either 1 or 0, and it switches depending upon a factor f And what the factor F does is it gives some indication of the stability of the ocean. It's called the stratification parameter, or the saltwater formation efficiency. And it's the thing in the blue box at the bottom. So that is the Ppo4 model, just 3 differential equations. A little bit easier to justify the various terms in this in terms of the way the Earth's climate actually works. And as I say, the key thing which makes it different from Saltzman and Marsh is this Heaviside function. In practice, it wouldn't be a rapid switch. It would be a switch over a few thousand years. But as I said, a few thousand years is almost instantaneous when you look at the 100,000 years of a typical glacial cycle. So that's the Ppo4 model. What are its predictions? Well, here I've done a plot of a sort of solution of this as a function of time. So the V is in blue, A is in green, C, the carbon dioxide, is in red, and this stratification parameter is in black. And you'll see as time increases, the ice volume V increases, and then it drops, and then it increases, and then it drops, whereas the carbon dioxide reduces, and then suddenly increases, reduces, and suddenly increases, and so on. So this is looking a little bit like a glacial cycle. It's even got the wiggles in it, which are consistent with the wiggles that we see in actual glacial cycles in between. So it doesn't look at all implausible. Okay, so that's the typical solution. From a mathematician's point of view, this is kind of why I got very excited in this. As I said, the Ppo4 model is an example of what's called a non-smooth Philipov system. And its structure is that if X is V, A, and C, then X dot is Lx, where L is just a linear operator, plus B plus or minus, plus the forcing from the sum. And the B plus or minus takes one value if F is positive and another value if F is negative. And this is a beautiful system. It's what's called a discontinuous dynamical system because you've got this change in state. And these were first studied by Philipov, a Russian mathematician back in the 1960s, who produced some general theory. And the study of non-smooth dynamics is an active area of investigation, a very active area of investigation at the moment in many other areas. Okay, so that's the sort of structure. There's a switching manifold, which is when F is 0, and that's when the carbon dioxide is suddenly released. And geometrically, what happens is that you have a trajectory which evolves, which is the sort of red trajectory. If F is positive, that would be in the glacial cycle. It then hits the blue curve, which is the discontinuity manifold, and then goes off in a different direction into the interglacial state. So you get this kind of classic curve of things where things change. The derivative changes discontinuously. Okay. The way to study the Ppo4 model is to creep up on it. So the Ppo4 model has solar forcing. We can switch that off. So that will correspond now to the Earth just evolving under its own dynamics. And that takes the form in the blue box, which is a non-forced, non-smooth differential equation. And this is a nice system. It looks quite simple. It's just two differential equations, linear differential equations glued together, but its dynamics is surprisingly subtle. When you study dynamical systems, the first thing you look at are what are called fixed points, which are points where x dot is 0, and the fixed points are easy to compute. You just put x dot is 0, and they're minus L inverse B plus or minus. And these would be called physical if suppose we're in the plus region, which is the glacial region, and F acting on it is positive, and if we're in the interglacial region, that's negative, and they're virtual if that isn't a curve. Don't worry about the technicality, but here is our one and only theorem of the day, which is that there's a critical parameter in the Ppo4 model, which is called D, which controls the different types of dynamics. And I had a long correspondence with Pallard about what D meant, and he wasn't too sure what it meant himself, but he knew that it was important. It's to do with the stability of the ocean layers. And if D is less than a critical value, then the Earth goes into an interglacial state and it's hot forevermore, which is certainly one state we've seen. If D is bigger than a critical value, then it's cold forevermore. And the most interesting is where D lies between these two critical values, and we see a periodic solution, which is the periodic solution we typically associate with ice ages. And the way it works is this. If D lies between these two values, you have two fixed points which try to attract the orbit, and an orbit starts from the discontinuity manifold from sigma. It goes into the region F positive, which is glacial, tries to get towards a fixed point which doesn't actually properly exist, switches over, and you get another cycle on the other side. And you get this really nice periodic orbit going from one side to the other. Okay, so that's what the Pallard model predicts. If you have no solar forcing, you have periodicity, just like the ice ages. And if you plug this in and take the values that are measured experimentally for these various parameters, this is what the periodic orbit looks like. You have a glacial state, which lasts for about 130,000 years, and then an interglacial state, which lasts for about, 15,000 years. And if you add those together, you find that the overall period of the Earth in this sort of system is 147,000 years, which is not 100,000 years, but not very far off it. And the Ppo4 model indicates that the Earth's internal variation is naturally 147,000 years and has glacial and interglacial states. So it isn't that. It's the Ice Age's period is more like 100,000 years. So what's going on? Well, what's going on? Oh, that's what the whole thing looks like. What's going on is that you've got the additional term in the equation, which is the variation due to the sun, which is the solar variation, which is approximately periodic and approximately has a dominant term, which has a period of about 41,000 years. Okay, so there is our actual system. And you can show that there do exist synchronized periodic solutions, which we call MN. So a periodic solution goes through M glacial cycles and N forcing cycles. And the period is then 2 pi times N divided by omega, where omega is the Milankovitch frequency. And here are two examples. The top one is what we call a 1-2 periodic orbit. So that is periodic and has a period which is 2 cycles of the Milankovitch forcing. And the second one is 1-3, which actually looks quite like a glacial cycle, which is 3 periods of the Milankovitch cycle. And here is our formula thing again. X dot is mu p sine omega t. So we've got parameters mu and omega, which we can vary. And if you look at mu and omega, and we look for the kind of existence of different types of periodic orbit, omega star here is the frequency of the periodic orbit without forcing, and omega is the frequency of the Milankovitch forcing. If you plug in the kind of values that we measure experimentally, So we know what mu is, we know what omega is from experimental measurements. You get the thing which is indicated by the star. And there are various other types of orbit around. So you've got the 1-3, which is basically what we seem to be seeing. The 1-2, the 1-1, the 1-4, and various other things floating around. So this is a numerically produced picture. And that picture took about 2 days to compute on my Mac, because there's so much going on. So things are not looking too bad, in the sense that we have something which looks quite like a glacial cycle, which is the 1-3 periodic solution of the Ppo4 model. And the physical values lie within the kind of range of existence of that. But what this model doesn't seem to explain at the moment is why we get the Milankovitch cycle. But not the Milankovitch, the Mid Pleistocene Transition. But there is a way of understanding this, if you look at this picture, because if you look at, there's a yellow region where you get the existence of the 1-3 type periodic orbits. There's a blue region where you get the existence of the 1-2 periodic orbits, and then there's a region in the middle where these basically overlap, and you can have both existing. So I'm going to kind of whiz forward a bit, and say if we fix mu at 0.5, which is basically where the physical region is, these are the various orbits that you observe as you vary omega. So on the right, we have the 1-3 orbit. Then there is a sudden transition down to the 1-2 orbit as you change omega, which changes to a 1-1 orbit as you do something else. And it's not unreasonable to speculate that if there were some variations in omega or variations in other parameters, that we might jump from a 1-3 orbit to a 1-2 orbit, or see something else going on in between. So this would be the kind of the forcing due to the continental drift that Saltzman and Marsh postulated. So to cut a long story short, here is an enlargement of the region where you get this overlap between the 1-3 and the 1-2 periodic orbits. And if we're in the kind of overlap region, then you get what we call a domain of attraction. So if you start the system off in one state, it will evolve to 1-2. If you start it off in another state, it will evolve to 1-3. And this is the domain of attraction. And if I start the Earth off in a state which is close to the boundary of these two, what we see is this picture. When Susan produced this picture in her work, I got very, very excited. We have an evolution over time from something which looks very, very like the type of ice age that occurred before the Mid Pleistocene Transition, then through what's called a grazing bifurcation. I don't have time to explain what that is, but an instability mechanism into the 1-3 orbit that we seem to be seeing physically at the moment. So that's really quite similar to the Mid Pleistocene Transition. If you add the extra terms into the solar forcing, which we know are there, the terms due to the eccentricity and the precession, then you get something which starts to look really, really quite similar to what we see in observations. So that's the Ppo4 model, which as I've analysed quite carefully. There's still quite a bit of work to do on it. But I wouldn't want to finish this talk with you thinking that I've answered the problem, because I definitely have not, nor of Ppo4. There are other models out there which also do a very good job of explaining what's going on. So here's one which I quite like, which was published by my friend P. Ashwin in Exeter in 2014, where he tried to replace the switch in the Ppo4 with what's called a fast-slow manifold. if anyone has worked in neuroscience and looked at the way that nerves work, Pete was trying to take a model for the nervous system and apply it to climate. So, so this was his model. Again, I won't go through detail, but there's perfectly reasonable justification for this model. Just to say that he has various parameters in it, and as he varies them, you can get sorts of motion, which are illustrated by these graphs, where you get the oscillations of small amplitude and short period suddenly evolving into large amplitude and large period. So that's Pete's model. It is, I think, a bit contrived, and he knows that. But there we have another model which predicts sort of what's going on in an ice age. So just to conclude, I've taken you on a journey through various different types of conceptual model for climate, and conceptual models aren't okay. They do give reasonable fit to observe climate dynamics. They're not perfect. They're not trying to do anything detailed, and there will always be averages rather than detailed, showing exactly what's going on. The sort of models that we get can either be studied using kind of classical mathematical techniques or some of the more recent developments in non-smooth dynamical systems theory. And as I showed you, the Ppo4 model does not a bad job of explaining the ice ages. But the big problem that we have is limited data. We've only got one data set of the Earth's climate at the moment, and it's relatively easy to tune any model to fit the data if you've got only one set of data to look at. So I don't think we're going to have a definitive answer to what causes the ice ages for some time yet. But still, there's a lot of interesting mathematics and a lot of interesting climate science to do on the way before we do. And at that point, I will finish and say thank you very much.
Okay, thank you very much, Chris, for such an exciting talk. So we have quite a few questions now. Okay, so I'll kick off with the first one. Very interesting. How good are the mathematical models for predicting the temperature, the future temperature, from the local point of view, geographically, I guess?
They're pretty good. So the IPCC, so the original temperature prediction models were, I suppose, people were writing these down properly in the 1980s, 1970s, 1980s. And they used these models to predict what the temperature would be now. And they've done a good job of it. They've been reasonably accurate. So some of the people that write nasty things to me saying climate models always get it wrong, why on earth you bother? And the answer is they don't. They do a reasonable job of predicting the temperature. The real difficulty is predicting the temperature and predicting how much carbon dioxide is going to be in the atmosphere, because that's a political thing and we just don't know. So if we carry on producing carbon dioxide at the rate we are, then we'll get one answer, and if we don't produce any more, then we'll get another answer. So it depends upon factors beyond our control. But one way climate models are tested is you initialize them with the Earth's climate in the year 1900 and then let them run forward and see whether they could predict the last century. And again, they do a pretty good job of that. And they're localized. The climate models are length scale 25, 50 kilometers, so they're reasonably good for local predictions.
Okay, thank you. The second question is, to what extent do mathematical models depend on associations and correlations first identified based on massive data analysis and simulations?
What a great question. Where do I start? All mathematical models for climate start from the laws of physics. So they all start from the Navier-Stokes equations for the atmosphere and the laws of thermodynamics, which were sorted out by Kelvin in the 19th century. So they all start with those, and they are massively tested every day by weather forecasts. Okay, so that's what a weather forecast is doing. A weather forecast is always also informed every day by taking measurements from satellites, and they're fed into it constantly. So a climate model starts with that, but then you have to build into it lots of other things, such as the chemistry in the atmosphere and the vegetation in the earth and the amount of ice you've got and the salinity of the oceans and so on. And that's coming from a lot of data measurements. But climate modeling at the moment starts with the laws of physics informed by data. There is a lot of interest at the moment as to whether we can just do pure data-driven climate modeling. And to be honest, it's showing some promise as a way of getting reasonable understanding of what the climate will do in sort of a few years ahead rather than a long way ahead. So that's kind of exciting, and kind of watch this space really, because that's where a lot of interesting things are happening at the moment.
Okay, thank you. What triggers the transitions between the stable states of ice-covered Earth and ice-free Earth, and why are in between states unstable?
Okay, so the main the big trigger, which we think is the real trigger, is the amount of carbon dioxide in the atmosphere. So if you've got a lot of carbon dioxide in the atmosphere, you'll have a hot Earth. And if you haven't got much, it's a cool Earth. So there are times in the past when the Earth was cool, largely because the sun was cool. You know, the sun goes up and down in temperature as well. And that was keeping the Earth cool. But then a lot of carbon dioxide was released into the atmosphere by volcanoes. And it was that which caused the trigger to go back into the hot Earth again. So it seems that carbon dioxide or other greenhouse gases is the big trigger, and always has been, which is why we're so concerned that carbon dioxide is going up so fast at the moment. So before the Industrial Revolution, the amount of carbon dioxide in the atmosphere was 250 parts per million. The carbon dioxide in the atmosphere is now more like 410 parts per million. So it's nearly doubled since the Industrial Revolution. And if it carries on at that rate, we're going to just get hotter and hotter. So that's basically the trigger, I would say.
Okay, thank you. The next question is, how long back, so how many years back does the ice register stretch? How many years back does the register of sediments stretch? And which data are more exact?
Well, there's also, I'm trying to answer that question very well. I will start with the first, a question which may be the one you want to ask, but I'm not sure it was, which is the register made by human beings. So human beings have been observing ice since about the 18th century, where sea captains typically would observe it from their ships. So we have human measurements of ice from about 300 years. Okay. Then if you have these proxy measurements, well, we can go back by drilling down probably about 10 million years, I'd say, reasonably well. Beyond that, we're having to look at other things like ocean sediments, and that will take you back further. Obviously, the further back you go, the less easy it is to sort of see what was going on. So people do graphs of the Earth's temperature going back right to the beginning. I don't completely trust them. But ice is nice because you can very easily read off the date, and you can make good, precise measurements, and you can calibrate those measurements against other things as well. So that is reliable. But there are, I say, these other ocean sediments. There's all sorts of ways of seeing what past climate was.
Okay. Yeah. The next question came from Josefina Diaz, who is asking if there is another planet of the solar system that has a similar behavior in terms of the temperature selection.
Okay, so that's a super question. So I said yes, there's only one data for climate, which is not true because yes, we do have other planets. So Mars we can look at. It's pretty clear that there was water on Mars, and then that stopped. We don't know why, but people out there do study the climate of Mars. Venus has gone into the hot state and has never come out of it. So its atmosphere is very heavily carbon dioxide, which is keeping it very hot. And of course, it's much nearer the sun, which is another reason. But what's wonderful and remarkable is that we now have good enough telescopes to look at the climate of planets going around stars which are not the sun. So there's a lot of work now on what's called exoclimate, where people are looking at planets huge distances away, but you can actually look at their climate. Incredible that they can do this, but they can. And the Met Office is now running some of its climate models on the basis of some of these planets just to see what happens. So I think this is just wonderful. This is very recent stuff, but really very exciting stuff.
Okay. The next question is from Juan Albert Sanchez. Wonderful talk. Where can we find a review of all the models and equations?
What a good question. So my favorite, I'll just type it in the chat, is a lovely review by a guy called Crucifix. So a few years ago, they had a program at the Isaac Newton Institute in Cambridge on models for climate, and Michael Crucifix, who basically runs a big research centre in France, that's me, Crucifix, wrote a review of all the kind of stuff that was discussed during that I&I program, and I think it's very readable, very easy to understand, and it's beautifully done. So that was about 10 years ago he wrote that. There's another book. There's a book by the various people, Henk Dijkstra, on which review that was published 2015, which is a review of climate models, which I think is very good. And then there's another nice book by Hans Karper, which is a Cyan book on climate models.
Okay, so, thank you. I think we will try to put this information in the description for the recording.
Yeah.
The next question is from Ligia Perez Cruz. Congratulations to Professor Bud, a masterclass. The climate is very complex due to all elements and subsystems involved. How accurately can we really predict it?
Well, there we go. There's the big question. Good question. So climate models are constantly evolving. So the climate models in the 1970s just basically looked at the sun and the Earth's temperature. And the ones we have now have huge amounts of stuff in them. And they're constantly being updated, putting more and more things in. So we're trying to do our best to include every factor of a very complicated thing. The best thing I can say is that when you produce a climate model, you also do a sensitivity analysis, which is to say, well, look, we don't know everything, but let's suppose I have a variation in some aspect of it. How much do my predictions change when I make that variation? And if they could change a lot, then we don't understand that process very well. And if they change not too badly, then we feel we understand it better. So there's no such thing as a climate model which is right. All climate models have a degree of uncertainty associated with them. And it's quantifying that uncertainty which is as important as doing the climate model. And when you talk to policymakers, it's extremely important. you put that in. The danger is when doing that is people think, well, if it's uncertain, it must be wrong, which isn't true. It just means that we don't understand it as well as we'd like.
Thank you. Incidentally, the next question seems to be linked to this one. So Emiliano Sanchez is asking, taking into account that it's been possible to model the behavior of these parameters, have there been any efforts to assess humanity's effects on them?
Yeah, very much so. So the crucial parameter is the emissivity of the atmosphere. And we know pretty well how well that's linked to carbon dioxide. And so you can do a straight sensitivity analysis looking at the impact of carbon dioxide variation on temperature. And that's very, very important part of climate modelling. There are other things as well, such as cutting down rainforests will change the amount of carbon dioxide in the atmosphere, and will also change the albedo. And other types of greenhouse gas, such as methane and to a certain extent water vapor. All of these can be assessed, and they are assessed, and that's a very important part of climate sensitivity modelling.
Okay, thank you. The next question is from Ligia. Is the release of methane gas considered in the models?
So yes, I mean so methane gas produced, for example, from permafrost melting in Siberia is very much included in the models. I mean, I didn't put it into the Ppo4 model because it's not considered important in the ice ages, but in terms of the modelling of what our climate is going to do in the next 10 years, is very, very much included in the models.
Okay, the next question is, in the 1600s, temperatures dropped and some say there was a mini ice age.
Yes.
Did human activity have any effect?
No, that was caused by the sun. So the solar activity dropped a lot. So there was a strong correlation between the temperatures and the number of sunspots. So the number of sunspots in the sun dropped to almost nil. The activity of the sun reduced. At the same time, there was volcanic activity in certain parts of the world, which was causing particulates to get into the atmosphere, which blocked the sun's radiation. So it was largely the sun diminishing in activity and the volcanoes blocking it out. So when the volcanoes stopped blocking it out and the sun started its heating up again, so we came out of what's called the mini ice age. And then we go into the warming period, which occurred through the Industrial Revolution.
Thank you. Do math models also predict extreme climate events?
Yes, is the answer to that. So what basically happens with the climate is the mathematical models predict that the Earth's climate will go up by a couple of 2 or 3 degrees. So you might think, well, so what? Daily temperature changes by far more than that. But that's changing the mean. And when you change the mean of something, it's like pushing the kind of probability curve over to one side, which means that the tails get a lot bigger. And then there's a strong association between the change in the mean and the frequency of extreme events. So if you look at things like the storms in the Atlantic, which obviously impact Mexico a great deal, then the frequency of those is related to the overall warming, and those sort of extreme events are very correlated here.
The next question is, how large are nonlinear effects in climate? Can a tipping point in Earth's climate occur in the near future?
Well, the answer to that is, firstly, the nonlinear effects are very important indeed. Secondly, will we have a tipping point? Probably not. We're nowhere particularly near a tipping point. If you actually look at the models we've got at the moment, you'd have to knock it quite a lot to get to a tipping point. So we are still in what I call small deviation. So I made this answer the question. Okay, I'll start again. if you look at the Earth's climate at the moment, the dominant things which are affecting us are perturbations to that, which are predominantly linear effects. And there's nothing in the IPCC models which indicate that we're anywhere near where the strongly nonlinear effects will occur. But the strongly nonlinear effects have certainly occurred in the past. And so the sudden release of carbon dioxide, which the Ppo4 model predicts, is a strongly nonlinear effect. So I hope that sort of answered the question. Yeah. I mangled it a bit on the way.
And what about the rapid warming in the glacial cycle? Is it triggered by a nonlinear mechanism? And
yes,
can it be considered a tipping point?
That's what I just said. So is it caused by a tripping point? Well, the jury's out. There are models which say it was a tipping point. I would say it was caused by this sudden switch, which in a sense is a tipping point, when the Earth's oceans became unable to hold the amount of carbon dioxide. So it was a strongly nonlinear effect, yes.
Okay, there are a couple more questions. Lithia is asking, models are mainly based on data obtained in temperate areas. How good are models in predicting temperatures in tropical areas? So temperate areas as opposed to tropical areas.
Well, no, we've informed by data taken all over the Earth. I don't think that's true. I mean, they take measurements. I mean, the hardest measurements to make are ones up at the North Pole. So right. I think the data's taken all over the place. It has to be.
Right. Okay. Oscar Garcia Miranda is asking, could non-smooth models be helpful in understanding COVID-19 and other disease cycles?
Well, they might be. We don't use them. So I'm spending all my time at the moment modelling COVID, and we're mostly modelling it using SIR type models, which are smooth, and it more or less seems to behave that. I mean, there are non-smooth effects in the sense that the sudden mutation and then rapid evolution of a variant such as the one we have at the moment, the Delta variant in the UK, because it's occurring so fast, is effectively a non-smooth thing.
Okay, thank you very much, Chris. I think this is it. This was the last question, and yes, indeed. So let me thank Chris again for his generosity, which I think has really been tested with the amount of questions, but they also show how motivating the talk was, I think. Yeah. So, well, with this, I'll pass over to Professor Meade. Let me just announce the next talk, which is Tuesday. The same time, it will be by Professor Yvette Fuentes of the University of Southampton, who will give us a lecture on can quantum metrology solve some of the biggest questions in fundamental physics. Professor Meade, over to you.
Thank you very much. I want to ask Mr. Urrutia if he wants to say something. He's serious. You want to say something, Jaime?
Well, just congratulations to Professor Bott. It's a very interesting research, very relevant, and just looking at the number of questions, well, it clearly generated a lot of interest. And we will be more than happy to keep in contact and establish the collaborations. We noticed that a lot of students were also asking questions, including how to join your group.
Well.
But so that will be good, and it's certainly one of the priorities of Fundación UNAM to have more students.
If I can just say, if you have any really good PhD students listening, I'm currently hiring postdocs to come and work with me. So if you go onto the Bath website, university website, you'll find the adverts for that. So I'll be very keen to have really good students to come work with us.
Oh, okay. Well, thanks very much. And this is good news. So we will certainly pass this to the students, and looking forward to have a more intense collaboration. Well, congratulations and thanks very much.
Thank you.
Thank you very much, Jaime. Thank you very much, Professor Paul. Thank you very much to our moderator, and thank you for all the time, or all the patience you had to answer all the questions we had. And that's a very clear illustration of how interesting was the presentation. Yo creo que tenemos que celebrar mucho que haya posibilidades de presentaciones como estas. Y yo creo que se inscribe justamente en este paraguas que hemos señalado de la nueva realidad. De cambio climático. El cambio climático y sus riesgos, sobre el que tantas veces se han expuesto sus peligros, la necesidad de avanzar más en la investigación, la necesidad de contar con más y mejor información como la que hoy nos presenta el profesor Bott, y que se suma a otras tantas alertas como la que nosotros tuvimos, por ejemplo, de nuestro premio Nobel de Mario Molina, que advirtió desde hace mucho cuáles eran los riesgos de no cuidar a nuestro planeta. Yo creo que tenemos que agradecer a la UNAM y al consorcio que tengamos la posibilidad de estas presentaciones. Y yo creo que los jóvenes podrán encontrar tanto en la UNAM como en las propias universidades del consorcio espacios para poder interesarse, para poder participar, para destinar su vida profesional a tantos de los campos que están asociados a estos riesgos. Economistas, matemáticos como el profesor Bott, ciencias de la tierra, ingenieros, biólogos, químicos. Yo creo que hay un amplísimo espectro de especialidades que pueden sumarse a este interés y que muchos más jóvenes se interesen por la ciencia dura. Felicidades a la universidad, felicidades al consorcio, felicidades a nuestro moderador y felicidades y nuestro agradecimiento a Araxi, que nos sigue presentando semana a semana presentaciones asombrosas que abren este horizonte de conocimiento, este horizonte infinito de la investigación científica y este campo tan amplio que puede contribuirnos a mejorar las condiciones de vida del planeta. Gracias a todos, felicidades a la UNAM, que sigue siendo, como hemos dicho, un faro de luz, y gracias a todos por esta presentación que nos ilustra la capacidad que la ciencia tiene para incidir en el avance en el conocimiento de los riesgos y del cuidado de nuestro planeta. Gracias a todos y seguimos en esta serie a la que los convocamos a participar el próximo martes, junto con las próximas actividades que tenemos en Fundación UNAM. El jueves, nuestros documentales por la ciencia. El martes, estas presentaciones que semana a semana hacemos. Ya tendremos una presentación posterior en donde se nos diga cómo se sumaron de muchos lugares de nuestro país y del planeta a esta presentación del profesor Bott. Y le agradecemos también su disposición para que siga contestando las preguntas que se le puedan hacer llegar. Gracias a todos y muy buenas tardes.